Okay, so we're going to be sketching this fourth degree polynomial. So we start by identifying the domain. Of course, the domain for any polynomial is just going to be all real numbers. And then we want to go ahead and do the first first derivative test. So we find critical points. So that's where the derivative is either 0 or undefined. Of course, our derivative is never going to be undefined since it's a polynomial. So we're really just looking where is the derivative equal to 0. So we could actually factor out a greatest common factor and then apply the zero product property, and we get that either 0 is equal to 4x squared, which gives us x equals 0, or 0 equals x minus 3, which gives us x equals 3. So we think about these values on our number line, and we want to check values in between in all these intervals, between less than 0, between 0 and 3, and after 3. What we're going to do is we're going to plug in these values into the derivative. If we pick a value less than 0, we get that the f prime is negative, so that tells us that f is decreasing on that interval. Between 0 and 3, it turns out that the derivative is also negative, so f is still decreasing. And then for values greater than 3, we get a positive derivative, which tells us that the function is increasing. So we have no change from decreasing to increasing here, but we do here. So we have from decreasing to increasing tells us that at 3 we have a local minimum. And that's going to be at 3 comma something. And to figure out what that something is, we're looking at remember this is a point on f. So we plug 3 back into f. And if we do that, it turns out we get negative 17. By the way, all of these computations, you should be double checking me for the sake of practice, right? Double checking that you get negative values here, positive here, all of these things, all these computations. Okay, so then now we want to do the concavity test, which means we want to find the second derivative. Second derivative here is going to be 12x squared minus 24x. Again, we want to know where is the second derivative, either 0 or undefined. This one's, again, never undefined, so we're just solving for 0. And again, zero product property. We get two values, 0 and 2. So if we consider these values on the number line and pick values in between in all these intervals for the second derivative, we get a positive result here, a negative result here, and a positive result here. So this is telling me that my graph is concave up, then it switches to concave down, then it switches back up to concave up. So we have two inflection points, right? Because we change concavity from concave up to concave down. So we have an inflection point at 0 comma something, and then again switching from concave down to concave up gives us another inflection point at 2 comma something. To find those values, again, we plug back into the original function. We're finding points on the original function. We get 0, 10, and 2, negative 6. Okay, so if we try to put all these pieces together, let's plot all of the points we see. We've got 0, 10. Then I've got, let's see, 2, negative 6. So here, let's set up a scale. 2, negative 6, maybe, right here. And then we have this point, 3, negative 17. So that's maybe down here. This is obviously just a sketch. I'm not really drawing it to scale here. If we wanted to go further and find intercepts, we would have to set the original function equal to 0. That's not going to be easy to find. So I'm going to just sketch without finding the x-intercepts. If you had to, you could use your graphing calculator. But of course, I'm trying to do this whole thing without a graphing calculator. Okay, so I know that I'm decreasing all the way from negative infinity all the way up to 3. So until I get to this point right here, I should be decreasing the entire time. Now, how am I doing that? Well, I'm decreasing in a concave up way until I get to 0. So let me draw something that looks like I'm decreasing in a concave up fashion. And then I'm going to be decreasing concave down until I get to the point 2. So something like that. And then I am decreasing concave up again. And I'm going to continue to stay concave up forever, but I'm going to start increasing now. So now I'm increasing and concave up. So based on this, I see I have an x-intercept somewhere between 1 and 2. If you were to look at it on a calculator, it happens at 1.61. And then it's not exactly clear where this would happen, but again, on a graphing calculator, that would be at like 3.8 or something. So, and there's our graph. So you certainly could double check that on a calculator. Notice that we have at 0, Notice that we had a place where the derivative was 0, right? We can see that tangent line, but it turned out to be an inflection point. And then we have another inflection point here, local min, etc. So there's that graph.